Welcome to the third class meeting of the EECE574, the graduate level probability and random processes. So here goes the post administration related material. First, since tomorrow is the last day for added drop period, read carefully the syllabus posted at the class homepage of the lab homepage, because we have two separate homepages, one in the lab home and the other is PLMS. Be careful, okay? Second, for your attendance, you have to use the electronic attendance system. And if you are present, but your system says you are late or you are absent, please let me know, okay? I remember I modified the last week's attendance, so you'll be all right for the last week. Homework 2 will also be assigned soon by this Friday, and due will be next Tuesday, so that you can spend your long weekend to review the undergraduate material, which is very important for the rest of this graduate course. Okay, we will heavily rely on the undergraduate material. So if you do not properly remind you of that, then you will be in a big trouble. So I push you a little bit hard in this beginning of the semester. Handouts and videos are available from the course webpage. And whenever you have enough time, please place clickable timestamps on the YouTube videos so that your friends or some other people who will later see the class meeting will be benefited, easily find the location where some specific topic is explained. Messages from instructor. Last week, I emphasized the importance of simplification and visualization whenever you confront any problem, your life, daily life problem, or your exam problem, or anything, your research problem. Try to simplify as simple as possible, but your simplified version should not lose the essence, the core of your problem. And then you solve that problem, even though it is too simple, so you must say it a toy problem. But solving the simplified problem, you will accumulate an experience to solve a little bit complicated problem. You will devise, so here is the original problem. You simplify until you can solve it. And then you solve it. By solving that, you accumulate your experience. And then you consider a little bit more complicated problem and try to solve that. You will be seeing that your previous experience will definitely help solving this problem. And then make the problem more complicated and up to the original problem. And suddenly, sometimes you will find that you have some intuition how to solve the original problem. And sometimes that makes you graduate, get the degree you want. And sometimes you further generalize the original problem. So you are given, for example, a specific research topic from your, for example, advisor, the professor. And then you solve it, and then you extend it further to become for example, better researcher. By the way, this is one of the approach a graduate student must have it. For example, your advisor may give you a very difficult problem because he has a lot of knowledge and he has a lot of experience, but he cannot easily calibrate your status. So he or she may give you a very difficult problem. Most of the worst cases is like this. In a week, your advisor asks you to have a meeting. And you go there and say that, okay, professor, I could not solve it. I couldn't do anything because the problem was too difficult. Never do this. It's the worst response of a graduate student. what you have to do is like this. Okay, professor, it seems the problem was so complicated, so I made it simpler and tried to solve it. And I solved it. And I made this progress. And if you give me 1 more week, probably I can solve the original problem or something similar to that. And in 2 weeks, probably your advisor was too busy and he or she will call a second meeting. And then suddenly you say that, okay, professor, I solved the original problem and made it more complicated and solved that. And suddenly you become so-called the golden boy or golden girl of your lab, okay? That is the dream, okay? So never forget this. Try to simplify and then solve it, accumulate your experience, get a lesson, and make it more complicated and complicated and complicated. In this way, you can always make at least some positive progress. Okay? That is important. Your advisor may misunderstood you if you say that I couldn't do anything. Probably he enjoyed a long weekend, something like that. So never do that, okay? And then another thing is this. Even though you successfully simplify the original problem, solve it, and eventually solve the original problem, you have to communicate in some way with others to publicize the results or have a meeting with, at least with your advisor. Whenever you have a meeting or you have a presentation or in a word, you have a communication scenario, try to visualize your result. Actually, that a lot helps you to well organize what you have to talk. And that is very, very powerful tool to easily communicate. Okay, so alternate visualization and simplification, and sometimes simplify, sometimes visualize. That helps a lot. Got it? Okay. Probably we will have more time to talk about this simplification and visualization later in this semester. Okay, here goes the overview. We are reviewing the chapters 1 through 6, which are all undergraduate materials from our in postdoc EECE574, which is named incorrectly mathematics for electrical engineers. But the contents are all about probability and random variables and random vectors and sometimes random processes. Since most of the undergraduate similar courses from other universities also have the limitation that they rarely teach random processes, this graduate course will have emphasis on the random processes. However, if we do not properly review the probability and random variable and the vector material, we can't make any understanding about the random process. So we are kind of very quickly reviewing the material. And then we will move to the sequence of random variables, which is an intermediate topic between random vectors and random processes. And then we will study some general concepts on the random processes and some of the topics, not all of these chapters, some of the topics from these chapters. For example, Markov chains and Markov processes and queuing theory are very, very important topics in advanced random processes course. However, I'm not an expert in that. Usually, the people in the computer network, they heavily rely on this part, but I most rely on this part, okay? And for example, if your professor advisor is doing some radar engineering, then he will be more interested in spectral representation and spectrum estimation stuff. I will talk a little bit about that. Okay, since we spent our weekend, so our memories are heavily reset. So let's review the material we reviewed the last time. The most important phrase in your undergraduate probability course must be the probability of an event of a random experiment. So this is the key phrase in the probability theory part. Okay, so the key phrase is the probability of an event of a random experiment. So this phrase contains all the important keywords you must know. First, what is an experiment? Experiments are there, scientific, random, but in this case, we are talking about random experiments, but we have to anyway define the commonalities of the experiments. One of the important commonalities is an outcome. We must, or we should have something, okay? It could be observable, sometimes it cannot be observable. However, we have some outcome. And also, this experiment must be some kind of activity. So we can conduct it, we can perform it. And also, repeatability is very important. That's what I told you. Especially in scientific experiment, if the experiment is not repeatable, then even though it's a scientific experiment, people have a lot of disputes. For example, these days, one of the most important results during last 30 years in astronomy, the topic of dark matter and dark energy is heavily disputed. Interestingly, already the Nobel Prize Committee have given the Nobel Prizes in physics to those discoverers. However, that theory is challenged. Why? Because it's very hard to do experiment on the cosmos. You cannot repeat Big Bang, even though you have a Big Bang theory, okay? But that's not the necessity. It's important. The repeatability is important in experiment. That's what I want to say, okay? I do not say that, okay, Big Bang cannot be repeatable. At least we are living or we exist as a human being, so it's not a science. I'm not saying that, okay? However, repeatability is very, very important. Second, in the random experiment, repeatability is also important because one of the reasons is that the meaning of probability of an event is based on the repeatability. If we can repeat, of course, independently, something like that, as probably you have reviewed the Bernoulli experiment or Bernoulli trials or sequential experiments, independence of multiple trials is very important, especially when we connect the probability, when we interpret the notion of probability as a relative frequency of some event. However, in some theory, under some certain circumstances, repeatability is not the necessity. For example, suppose you mathematically construct a random experiment of rolling a die. Then you may assume mathematically that the die is a fair die. Then, even though you roll a die just once, you may definitely say that the probability of event you are seeing the outcome 1 is 1/6. You can say that, even though you just try just once. Got it? However, in order to have that probability to have some physical meaning, repeatability is very important. Anyway, the second is that, so random experiment is an activity that has an outcome with uncertainty. Repeatability is very important there, okay? And what is an event? It's a kind of collection of outcomes. So you may say that what is the probability of an event such that I observe even numbers when I roll a fair die, something like that. So that event consists of more than, it can consist of more than one outcomes, okay? Of course, it can consist of single outcome. And the probability, as I told you, is a kind of size of the event. And we assign the meaning of the size of that event, the probability, okay? And it's closely related to the relative frequency. However, the relative frequency interpretation of the probability, though it's very important and intuitive, it has serious drawback because especially when we consider some conditional probabilities, it's like posterior probabilities. Like, okay, I want to compute now the probability of such an event, given another event already occurred. People have a lot of disputes, especially if you take a look at the so-called Monty Hall game or Monty Hall problem. There are many people, if you Google it, many people, they just argue and saying that the probability of your getting the BMW does not change, still 1/3, something like that. There are tons of arguments, even though we already have developed the precise theory, okay? So given that, without very precise theory, we can't even come up to the conclusion, given a mathematical problem. So people develop the theory, and the theory heavily relies on the set theory and also so-called measure theory. Fortunately, from the set theory, we just need to some of the terminologies like an empty set or the empty set, you may say that, and the classification of sets, countable sets, uncountable sets. Also, the terminologies like universal set, subset, power set, complement, union, intersection, especially countable set operations is very important. Countable set operations of these complementation, union, and intersections, because we are going to use the notion of a sigma algebra for our event space, the set of all meaningful events. So that is very important. Of course, the Morgan's rules, Venn diagrams are very, very important concepts from the set theory. By the way, what is a sigma algebra of subsets of a set in the probability theory? Of course, this sigma algebra notion comes from general set theory. However, in our probability theory, let's just think about a sigma algebra of subsets of the sample space, because we have a concrete concept of sample space that consists of every possible outcomes, or even some bigger set that includes all possible outcomes. Anyway, so what is a sigma algebra? Sigma algebra is, in order to talk about sigma algebra, we have to have a non-empty set like 1, 2, 3, 4, 5, 6. And then a sigma algebra, which means that from that set of 6 entries, we can construct different sigma algebras. First necessity is that a sigma algebra must contain the empty set and this original universal set. And also, a sigma algebra must be closed under countable set operations. So as an example, I told you that just a second, I do not like this color. Okay, given this, some sigma algebra may just contain the empty set and the universal set only. Still, this is a sigma algebra. Let's say this is sigma algebra 1, and we can construct sigma algebra 2 that has something like this. This is sigma algebra, because you can easily check that whatever set operations you conduct on these 4 events, then still you have an event in this event space, okay? And then the problem is that you are very tempted to use the power set of the sample space as a sigma algebra. And last time, I little bit made a statement that confused you. So let me have a correction. So correction or clarification. Power set is a sigma algebra. However, that's too big. That's the correct statement. That's too big to be used as the sample space, okay? Anyway, so what I'm saying is that even though you can consider a power set of the sample space as a candidate event space, mathematicians have found that that's a too big sigma algebra, okay? So as we will see today, when we talk about random variable, we will have a much, much smaller sigma algebra, okay? That is powerful enough, large enough. That's very small, but large enough, something like that. Anyway, and then we mathematically model a random experiment by using a triplet consisting of the sample space and a sigma algebra. Sometimes I will just say that the second component as a event space, but precisely speaking, event space is a pair of the sample space and sigma algebra. However, I will just say sometimes the sigma algebra as the event space. Okay. Anyway, so we model a random experiment using a probability space consisting of the sample space and a sigma algebra of subsets of the sample space and a set function P. And this P is very interesting. P has a domain E. So this sigma algebra is the domain of this set function. And this set function maps an event to a real number. But not only that, it must satisfy three requirements. And we call these three requirements as three axioms of probability. First one is what? Non-negativity. The probability must be non-negative. It's greater than or equal to 0. Second one is bounded by 1. So the probability of the sample space equals 1. And then the third thing is very interesting, is countable additivity. And countable additivity combined with the closedness of our event space under any countable operations of countable set operations enables us to compute any probability of an event in the event space. Okay, so that's what mathematicians have found. So if you really want, I hope not, but if you really want to dive on that theory, go to the math department, take the mathematical analysis and take the measure theory course, and then take the probability theory offered in the mathematics department. And then you will have a very, 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 very solid foundation in graduate level probability theory, okay? Actually, that is what's going on in the graduate school of electrical engineering in the United States. So suppose you joined, for example, Stanford University, you joined MIT, not only that famous universities, some also very prestigious universities like Purdue, Michigan, their advisors all ask you to take these three courses. If you are majoring in signal processing, communications, radar signal processing, even computer, in some area of computer science. So that's very important. But anyway, I'm not going to require that in this course. An interesting notion is that once you have defined mathematically a random experiment using a probability space, then by taking any event from the event space whose probability is positive, you can generate another new probability space called the conditional probability space. And what's the meaning of that? It's kind of posterior probability of the event given your choice of event occurred. And that is very important. And that also gives you some interesting formula like this. So suppose you have defined the conditional probability measure as something like this, where the start is in the event space, right? And that is, of course, sometimes you can just say Q, but in that case, we easily run out of the alphabet. So we usually introduce this notation. Okay, and this is called the conditioning bar. Some people conditioning bar. Okay, and with this definition, we easily have some formula like this. If the probability of B is also positive, we can say that we have something like this. This is called chain rule, and it can be extended to many, 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 many intersections, not only two, as you remember. And this also gives us some interesting formula like this. The ratio of the conditional probability to unconditional probability is always the same. And this formula is not emphasized much in the undergraduate and even graduate courses, but it's very, very important when you take information theory. Okay. This is due to the symmetry between A cap B and B cap A. This number can be greater than 1, equal to 1, less than 1, especially when it has it satisfies equality. That's very important because what? The conditioning doesn't matter. The posterior probability in Korean 사후 확률 equals the prior probability, 사전 확률. So this conditioning doesn't matter. It does not alter the probability of event A before and after the occurrence of event B. And same thing happens to the event B. Okay, there is a symmetry. And later, this gives us the notion of independence. So two events are independent means that their joint probability or intersection probability factors to unconditional probabilities, A and B. According to this definition, the left-hand side must be what? As I have written, this or that. However, what does this mean? Conditional probability of B given A equals probability of B, and conditional probability of A given B is also A. Got it? So this is the case of independence. And what's the meaning of that? Any event that can be constructed from the event A, but you have only two, right? A or A complement. Any event that can be constructed from event B by using countable set operations, those are B and complement of B, they are also independent. So this implies you can easily show that A complement have B is A complement, PB, and other three equalities. Okay. Similarly, you can extend the idea of independence of two events to independence of two groups of events, which means that you have one group of events, you perform any set operation to get an event, one representative, and you have another group of events, you do some set operations to get another event, then they are independent events. Whatever set operation you have, that's the notion of independence of two groups of random variable, not random, two events. And then you extend the knowledge, this new concept to independence of three events. And what is important is that if you have A, B, C events independence, then any pairwise independence must be met, and the intersection events P, A cap, B cap, C equals the product of individual probabilities. So be careful. Later, after you learned multiple random variables, suddenly I say that pairwise independence is implied by the independence kind of factorization of the joint probability to marginals. And you may say that, hey, you are talking two different things. Actually, I will not be, and I'm not. When you talk about independence of, for example, three random variables, it's enough to say that joint probability density factors into marginals. You don't need to talk about joint independence, because three random variables independence implies two random variables independence. And this factorization implies factorization of two things. However, when you talk about events, it does not hold. So be careful. And then, so far, we have defined the conditional probability, just the notion of conditional probability measure, and suddenly we have theorems. One is the total probability theorem, that is to compute the probability of some event by introducing a so-called partition of a set that includes the original event. Most often you introduce the partition of the sample space, but that is not necessary, as I emphasized last time. Second one is the Bayes theorem, and this is one of the most important things, but actually it's simple combination of the total probability theorem and definition of conditional probability. You have to remember but the meaning. So if you want to compute something like this, so you want to compute the conditional probability of event A given some event B, but I will just name B sub M, then what do? You have, just a second, not this, sorry. Yeah. So from the definition of the conditional probability, or you just say that from the chain rule, you may say this first, because if you move this one to the left-hand side, you have the equality, right? Ratio and ratio. And then you introduce a partition that includes B sub m as one of the components of the partition of omega. So what you do is that, sorry, not omega, I would say the sample space S, and you have, be careful, I used index n, something like this. Okay, so I have the base theorem. Interesting thing is that we usually remember from our undergraduate and even high school math that, okay, what is the base theorem? What is the conditional probability? Meaning you can change the order between these conditioning bars, something like that. That's visual memorization method, right? So you want to compute the conditional probability of Bm given A, and eventually you have or conditional probability of A given Bm and Bn, right? So that is one way. However, you have to remember the meaning or physical meaning of that one. Anyway, that's the idea. And also we can introduce the notion of conditional independence by combining the notion of independence and notion of the conditional probability measure. And that's not that difficult as far as you have a solid foundation. And then finally, our topic was what? The combined experiment. Because in most of the engineering problems, we have a lot of experiments serially or parallelly connected. So we first need to define the sub-experiments first, and then combine them dependently or independently to construct a new experiment, the biggest experiment called a combined experiment. Okay? And the combined experiment also is a random experiment, so also has a probability space. And the sample space can be easily said that it's the Cartesian product of all the sample spaces of the sub-experiments. However, when we construct an event space, we still, again, must be careful. So it's not just a simple Cartesian product of event space, because sometimes that Cartesian product of sample event spaces may not be a good sigma algebra to be used as the event space. And the probability measure is also sometimes simply multiplied in the independent combining, but as you've seen in your homework problems, especially that Monty-Hall problem, the experiments, multiple sub-experiments are combined dependently, so you must be careful. One good thing is that, which is not covered usually in my course of the previous years, that we can easily use a tree or trees to compute the conditional probabilities or marginal probabilities when the sub-experiments have finite sample space. Okay, so when we have finite sample space, which means that sample spaces are finite sets, then we can just draw trees to compute the probabilities and conditional probabilities. So even though my previous quiz problems or exam problems asked you to just use the definition of conditional probability, total probability, and Bayes' theorem to compute certain conditional probabilities occurring in the Monty-Hall problem, try to redo that by using a tree diagram. That greatly helps you, okay? And you will understand what does this mean. In the root branch, you put probabilities. And then in the branches that connects some dots and other dots, you use conditional probabilities. And then in order to compute the final probability of the leaves, then you need to multiply, you need to choose as one path from the root to the corresponding leaf, and then you multiply all the numbers appearing on the path. And then that will give you the unconditional probability. However, if you want to find some conditional probability of this leaf event, given some midpoint event, then start from that midpoint and then end up at the leaf. You multiply all the conditional probabilities, then you have the final conditional probability of the leaf event given some specific midpoint event. Got it? So that's important. And about the counting methods, I just emphasized one thing. Usually, people do not use this notation, even though we and Japanese people love this notation. In the US, they use something like this, okay? And they read it and choose R. Okay, be careful. Okay, here goes the preview. I reviewed it more than 30 minutes, but that's very, very important. So let me quickly preview what we are going to cover this week and probably, hopefully today, but definitely I cannot. The first one is the notion of a random variable. That's the kind of, you may think it's a special case of a random experiment where your outcome is a real number. Okay? You understood in this way when you are an undergraduate student. That's correct. That's okay. However, we want to use more major theoretic terms like probability space and such. So we will little bit improve our mathematical model. And there goes a classification of a random variable. One is the family of discrete random variables, and probably you already know. The other is continuous random variable. However, there are combination of these two called a mixed random variable. And unfortunately, I've searched some reference, and they say that the random variables are classified into 4 because there is so-called singular random variables. Actually, I do not know, and even though even the reference said that it's not that important, forget it if you are an engineering student, something like that. So I will not talk about this fourth one. We will talk about these 3. And we will also review the notion of CDF, notion of, not this one yet, the probability density function, and some conditional CDF, conditional cumulative distribution function, conditional probability density functions, okay? And also, as we've done in the previous probability theory part, we will not only talk about conditional something, we will also talk about total probability theorem, revised for random variables, Bayes theorem, revised for random variables, independence, revised for random variables. Got it? Okay, so this is the lecture note of my undergraduate course augmented by this first part. So except this, the third page, fourth, up to 8th page, the last part is just a repetition of probably 2 years ago my lecture. So if you want to review these parts, starting from 2.0 up to 2 point something 9, yeah, just go to EECE574 of my homepage, and there are links to the videos and also PDFs. Okay. Okay, so let's see what's going on. So as I told you, the undergraduate version of the notion of random variable is simple. You have a random experiment and your outcome is real. So S is a real number. Then it's a random variable. But they said that, okay, this is a lowercase letter s, right? However, we don't like that. So we just say that, okay, let's say output is x, a variable, because when you perform different, for example, independent experiments, you will see different numbers. So when we name the output, it's a variable. It's not a single constant, right? It's a variable with uncertainty. So calling this as a random variable makes sense, okay? So random variable really appeals to our intuition. However, there is some confusion like this. Suppose here is me and I have a dice, and whenever you just touch this box to inform me that give me an outcome. I roll a die and give you the number. Suppose my output is 5. Then what do you say? Do you say x is 5? Something is strange. So what people did is like this. They use capitalized letter and also uncapitalized letter. And they said that, okay, this is individual outcome, and this is the outcome with uncertainty. So they say that, okay, x equals 5 means that I have a random variable x, and the outcome is 5. Actually, that is an event. Okay? So this event occurs when I give you 5. Okay? So this means event. However, as you've seen already, people just say, for example, PR of x equal 5, not PR, the probability of event x equals 5, something like that, because it's just inconvenient. Okay? So there goes a lot of abuse of notation. However, precisely speaking, your event must be a set. Okay? Your probability measure must admit a set, an event. Okay? So we must have something like this. Not here. Okay? Not yet. Okay? So we need this curly bracket to denote it is an event. Okay? So this means that probability of the event that x equals 5. The random variable x has the outcome 5. Okay? You know what I mean, even though it's not mathematically precise. Okay? And that was one of my questions when I took the undergraduate course, because this notion of random variable didn't fit to any previous knowledge about mathematics. So it was very strange. However, in our graduate version, we have much better approach. So it's like this. Suppose we are given a random experiment consisting of sample space, event space, and probability measure. And its outcome is S, lowercase s. Okay, nothing capitalized yet. And then here goes some function, a mapping rule named x. Okay, and this mapping is very interesting. This x maps any element in the sample space to a real number. Okay? Of course, given a probability space, there could be many, many different such mappings. However, suppose given. And then what is the output? You must say that this is capital X over S, right? Because you learned something like this. Here goes X. Your output is f of X, right? This is what you learned in your high school, middle school, even undergraduate school. So this idea of defining a random variable as a mapping rule appeals to our knowledge in mathematics. So actually, in mathematical probability theory, a random variable is simply defined a function defined on the sample space and the real number as the codomain. That's it. The problem is that, as you see, in this rolling a die experiment, right? Do we really have to divide it into something like this? And you may say that. However, what people do is that they enclose these two and then call this output by dropping this parenthesis s and saying that we have a random experiment that generates a real number. Okay? So actually, this one means that one with parenthesis S, okay? So this is now, this notation or this figure, entire figure, must be understood in this way. So this is an abuse of notation for that. By the way, this random experiment is called so-called the underlying random experiment. And this probability space is called the underlying probability space. So random variable is now simply a mapping rule. Especially, it must be a measurable function or measurable mapping rule, where it is, see, yeah, measurable. And what does this mean? This has meaning in this way. Before, we had the notation like this in your undergraduate, even a research paper, but precisely speaking, this is a very, very, very abuse of notation. Because whenever we talk about probability, we must have a probability measure, which is a set function. And no set function has this name because every different random experiment has different probability measure. But usually we just say probability of X less than X, probability of capital Y less than lowercase y. So whenever we talk about probability, we usually use P sub R, PR, right? This is an abuse of notation. So one of the reasons why the probability theory was so complicated is that our undergraduate, high school, middle school, elementary school probability courses used a lot of notations that is abused from the precise notation, okay? So what does this mean in terms of this probability measure of the underlying probability space? That is probability of the event that S in the, sample space. So it must be S, let me correct it. Such that when S is evaluated, mapped by the random variable X, it's less than or equal to X. So see that this probability measure must measure a set of S, right? In the sample space, right? In this set must be an event of S. So this is the precise definition of this abuse of notation. And here measurable means that this set, this event, can be evaluated by the probability measure of the underlying probability space. In this sense, actually, if you are not going to talk about measure theory, you can just drop this measurable, the term measurable, okay? So you may just say that a random variable is a function from S into R, okay? From sample space to a real number, so that you have a real number. However, in some random experiment, in engineering sense or in reality, we sometimes we want to extend our outcome to the extended real line, which includes plus and minus, or actually positive and negative infinity. For example, suppose you have a rolling die experiment, okay? And if the outcome S is 1 through 5, then you give me this specific number times 100 US dollars, okay? But if the outcome is 6, you do not give me any money. And we define X as the, no, that is not good. You give me, for example, $100 in 1 minute, in 5 minutes, but if you observe 6, you don't give me. However, let's define X as the time you give me $100, which means that there exists a probability that outcome is infinity, right? Because you don't give me any $100 by any time. So sometimes in engineering sense, Like sometimes you construct a finite state machine and that is just stuck to a state, right? And then just it does not come out from this state. It's possible due to some bug or intentional programming. In that case, if our outcome is measured as the time of some event occurs, then we must allow infinity, positive infinity. And for the technical reason, sometimes we want to assign the outcome of an experiment as negative infinity, actually, which means that the large enough past time or some number, or small enough some real number. Be careful, whenever as an engineer, we talk about plus or positive infinity or negative infinity, we want to actually say that for sufficiently large something, actually no infinity. However, there really exists infinity in some cases if we precisely define. So be careful. Anyway, so sometimes x is a function from sample space into the extended real line that includes so-called plus minus infinity. Okay, so R bar is R union plus infinity minus infinity. Sometimes. However, in many cases, if we have outcome plus minus infinity, we have a lot of headache. So what we do is that we simply assign that plus infinity to a large number. For example, suppose you roll a dice, and sometimes, as you've seen in some Hong Kong old movies, for example, in some game, you must have 0 in your outcome to win the game. And then your hero does what? Suddenly, he makes the die broken, something like that, right? And if that occurs, you may assign it to 0, right? With small probability, like 10 to the negative 6. And all the others as the 1 minus 10 to the 6 divided by 6, something like that. So what usually do is that they assign some finite but very big number or very small number when they introduce. They have to allow plus minus infinity or some very large number, very small number. But anyway, your undergraduate course usually, even graduate courses, talk about the case where our range of this random variable is a real number, a finite real number. Be careful. There are 2 cases. Outcome allows is plus minus infinity or a finite real number. Anyway, so first thing, anyway, what I want to say is that even though in your undergraduate program, your professor draw this figure to explain the random variable, that is actually this, okay? That is the key. So you have to remember this thing, okay? And also the term underlying random experiment and underlying probability space. The reason why people say underlying is that actually we don't need this idea. As far as we understand, a random variable is simply a mapping rule. It's not something strange. Outcome with uncertainty, that is not random variable. Random variable is a function that maps the outcome of an underlying random experiment to a real number. Okay, that is the precise definition. Now, let's see why we don't need to understand, or our undergraduate program didn't talk about the underlying probability space. This is why, because whenever you have an underlying the random variable, let me show you. So here is a sample space, event space probability measure, and here goes S, and here is a mapping rule, and you have the outcome. Anyway, the behavior of this entire box is, as we learned in our undergraduate program, is a random experiment that generates a real number as an outcome, right? So just observing its behavior, outcome, without thinking about its structure, internal structure or mechanism, what it is, we must have some probability space that generates a real number. So your sample space must be a real number, right? And you must have some event space, and you must have some probability measure that is not P. Let me call P sub X because it's kind of induced, derived from these two systems interconnection, right? So let me call new probability measure as Px. And what would be this one? Of course, depending on the random variable. So if we consider different random variable, like, okay, let's toss a coin. Okay, that would be very simple. So you have heads, tails, and 2 to the s, and some probability. And here goes s, that is either h or t. And then here goes your x that maps h to 1, t to 0, right? So what is the probability space? What is the probability of this random variable? So let me say that what is the probability space of this experiment that generates either 0 or 1? Your sample space, you can say 0, 1, and 2 to the 0, 1. And you may say that, okay, this probability measure Px must satisfy what? Px empty equals 0. Px 1 is, for example, 1/2 equals Px 0. And Px 1, 0 equals 1, right? This is the kind of the sample space of the induced probability space. This would be the sample space, event space of this induced probability space, and this Px is the probability measure of this induced probability space, you may say. However, people have found that you don't need to use a specific sample and event space. Whenever your outcome is real, you can just use R here instead of 0, 1. Because anyway, your sample space does not mean that any element of the sample space must have a non-negative probability. It could be something else. For example, in this case, you may define a new event space and precisely define some induced probability measure. Anyway, you can satisfy this property. And then what would be this one if you choose R? 2 to the R, as I told you, is too big, okay? The power set is too big. And people have found some notion of the Borel sigma field or Borel sigma algebra of R, okay? What is that? In order to understand this one, we first need to define a sigma algebra generated by some subsets of the event space. So here goes the idea. So suppose you have, let's start directly from this R. You have the real number as the sample space, and you choose some events, like something like this. Some open sets, for example. So your new family of events have these open intervals, for example. And what does that mean by a sigma algebra induced by this family is this one. The sigma algebra must contain all the events. Okay? And the first necessity is that one. However, you will easily see that, you can easily show that such sigma algebras are many, many. And then what you do is that you intersect these sigma algebras to have kind of the smallest sigma algebra containing all these events. That is called the sigma algebra generated by this family of events. The Borel set is this. Consider set of something like this, A, B, and A, B, R. Okay. Then what is this one? This is a subset of intervals in the real line, right? And then you find the sigma algebra that contains all these intervals. And there are many, many, many such sigma algebras. You intersect these sigma algebras to find the smallest sigma algebra. That is called the Borel sigma algebra. So here goes the Borel sigma algebra, denoted by B, is the sigma algebra generated by all open intervals over. Got it? And this sigma algebra generated by means that you need intersection. So you have the smallest sigma algebra. Anyway, so mathematicians have found this one. Whenever you talk about a real random variable, you don't need to, not always, but you don't need to care about your choice of sample space and event space. Just choose R and B. Okay, so here you choose just R and B. And then, sorry, not here. Oops. But just carefully choose your induced probability measure. That's all. That's enough. And there is one interesting theorem, again, I'm not going to prove. In order to choose this Px, that here you can have some set A that is an element of the Borel sigma field. If an event A, of course, it can be an open interval, right? If this event is this subset of real numbers is in the Borel sigma algebra, this is called a Borel set. Okay, this one is the Borel sigma algebra, and this is a Borel set. For a Borel set, then what? What you need is that you only need something like this. So as far as you specify the value of the induced probability measure for an interval like this, from -infinity to x included, then it's enough to fully specify any induced probability of event A, a Borel set. Actually, that is the reason why we use the so-called, probably you already know what does this mean, the CDF, okay? The cumulative distribution function. Actually, this is the cumulative distribution function of random variable x. It's enough. We don't need anything, actually. We don't need the notion of underlying probability space and the mapping rule. However, in order to understand what is a random variable, we need that model, right? We have to have an underlying probability space and a measurable mapping rule, because this is the random variable. However, if we view this entire random experiment as a single thing, in order to describe a new probability space for this single random experiment, we don't need to specify the sample space and event space, because mathematicians have shown that choosing R as the sample space, choosing the Borel sigma algebra as the event space is enough as far as your induced probability measure is well defined for the set -infinity to x, which means that as far as you define the CDF, cumulative distribution function of the random variable, you are done. Okay? That's why your undergraduate course never or just little talked about this underlying probability space and those things. Got it? Anyway, this lemma and theorem is very important. They too links the major theoretical probability theory to undergraduate especially engineering probability and random process. Okay? So as far as no point mass at plus minus infinity, evaluation of this interval using an induced probability measure is enough. And this is nothing but the CDF. So CDF is very important for random variable. Okay, now let's divide all possible, the set of all possible random variables into 4, even though we mostly talk about 3. So here is a set. Let me use a Venn diagram. This is the set of all real random variables. Of course, we will learn about complex random variables. So I say real, but here it's just real, but all random variables. We divide into 4, like this, but one is very small. First one is discrete random variables. Second one is continuous random variables. Third one is mixed. And last one is all the others, including singular and something like that. Then what is a discrete random variable? Your outcome, if you really collect the outcomes, not just the real number R as the sample space. So if you collect that, that is called the range of random variable, okay? So range of random variable means that you really stand there and see the outcomes in many independent trials, and you collect these possible outcomes and form a set that is, let's say, S sub x, okay? And that is called the range of a random variable. If this set is a discrete set, which means that it's a countable set, then you call this random variable a discrete random variable. Got it? So very simple. If it is a discrete, then you just need to specify only the atom's probability, induced probability. That's it. Like, for example, you have 0, 1 case like that. You just need to specify these two. Then what is that one? 0. From what? From the axioms of probability, right? What is this? 1, right? What about your rolling a fair die experiment? You just need to specify the atom's probability. And then any probability, induced probability of some events of the outcomes of this random variable experiment, you can compute from these things, even in case where these numbers are different, not just 1/6. Atoms probability is enough to describe, fully characterize the induced probability P sub capital X. Okay. So we define a function called probability mass function for a discrete random variable. And let me use lowercase p with subscript capital X. That is strange, but this is a kind of standard notation. So P sub capital X means probability mass function of a discrete random variable X. And this is defined as that value, the induced probability measure of the event, an atom event or elementary event, X. And X is in the range. Okay. So now we can say here simply lowercase p sub x over 1 equals 1/6. We don't need this capital P and curly brackets. We don't need that, okay? So PMF is very convenient in describing the probability and probability of events of in a discrete random variable. By the way, given this set of discrete random variables, of course, there are families of random variables. And these families are usually parameterized by only a few parameters. Just consider a case where your range is 1 through 100, all natural numbers. How many different random variables do you have? Uncountably infinite. Why? Because this requires what? Describing this value to this px 100, and each one just needs to be non-negative, less than 1, and their sum just needs to 1. How many such vectors do we have? Uncountably infinite, right? So it seems that it's not easy to group our discrete random variables, even though we just fix our range of the discrete random variable. However, there are, of course, some families like this. For example, in a Bernoulli P random, so let's consider Bernoulli random variables, which are parameterized by a single parameter P, positive and less than 1. What is this? The outcome is 0 or 1. And probability of outcome 1 is P. And P can be any number. So we have uncountably many different random variables, but they have commonality. We have geometric random variables, also parameterized by single parameter. And what is geometric? So first the value is what I remember. It's related to geometric series, and I remember first value is 1 minus P, and the second value is 1 minus P times P, something like this. So Px, let me see, Px, just a second. Yeah, sorry, something's wrong. Yeah, something like this. So if you add up all the countably infinite positive numbers, then you have 1 from your geometric series, right? As you remember from your high school math, if the first term is P and your ratio, common ratio is 1 minus P, then what? You have 1, right? So these probabilities of each atom is related to the geometric series. So this is called a geometric random variable. So this is parameterized by a single parameter. So we have a family. We have another family of binomial random variables with 2 parameters. N can be, by the way, here P is interpreted as the probability of you observe, for example, something occurred, or probability of 1 if you observe something. If it is 0, then you try again, something like that. So there are many, many different interpretations to this geometric random variable. In binomial case, as you already know, you try n times independently, and how many, for example, ones occurred, something like that. So the family is related to that one. There is so-called Pascal, discrete uniform, Poisson, and especially this family of Poisson random variables will be used in our description of a family of random processes later. So if you do not remember, just review this one carefully. Now here goes the notion of CDF, which I already talked to you. So CDF is simply the probability of the event that your random variable takes a value, outcome, realization. This is called sometimes realization or instantiation of the random experiment that is called random variable. So it's this probability, or you may say that in terms of the induced probability measure, the CDF is defined simply as the induced probability of the interval negative infinity to x, okay? And as I told you, according to the theorem, we are not going to prove the CDF is enough to describe a real random variable. But be careful, a real random variable without any point mass at plus minus infinity. If we have infinity, then we have to little bit revise this one to for this one to define from R bar, which is the extended real line. But in our case, no point mass at plus minus infinity, so it's simpler. What is the property of a CDF? Non-decreasing, right? Continuous. Be careful, not necessarily continuous. It may contain jump discontinuities, not necessarily differentiable. So its differentiation may not be well defined. However, by introducing direct delta functions as we learned in signal-gen systems, we can define somehow the differentiation of discontinuous CDF. So we have these properties. Interesting result is that if X is a discrete random variable, its CDF is what? Piecewise constant. And of course, right, continuous and non-decreasing. So something like you have flat, jump, flat, jump, flat, and at each flat in the area, you have right continuity, which means that if you have some jump discontinuity, then this point is included and that point is not included in your point of view, something like that. An interesting thing is that then what is a continuous random variable? Continuous random variable is a random variable whose CDF is a continuous function. So in terms of CDF, you can say that if it is piecewise continuous and satisfies the general property, then it's a discrete random variable. You don't need to introduce the notion of range of the random variable to classify a random variable as discrete. You just use CDF and say that if it is piecewise continuous, then random variable is discrete. If it is continuous function, sorry, it must be a continuous and monotone increasing. Continuous function, then it's a continuous random variable. Got it? Okay, let me quickly say that, of course, there are families of continuous random variables called uniform exponential, Erlang, Gaussian, a lot of things. And especially Gaussian is very, very important. And even though some people use parameters like mu and sigma, some people love mu and sigma square. So you must be careful, okay? Okay, PDF, what is a PDF? PDF is defined as the derivative of CDF. However, as I told you, a CDF is not necessarily differentiable. So what we do is that as an engineer, we introduce direct delta functions. Okay? However, precisely speaking, PDF is not mathematically good entity, even though we use repeatedly. Got it? Anyway, it seems we have run out of today's time. So let me resume from the PDF next Thursday. Okay, that's all for the day.